In this video, we want to determine the optimal thickness distribution for this open hole coupon. What we are going to consider are the von Mises stresses for both load cases 1 and 2. Now, traditionally, you might be tempted to use topometry optimization to perform this thickness distribution optimization, but there's one big problem you get. Whenever you constrain element responses like element stresses, strains, if this was a composite, failure indices, apply stresses, and things like that, the solution is often a discontinuous solution. So here in this example, you see what the thickness distribution will look like if you perform a topometry optimization. In this short tutorial, I'm going to show you how to get something that's a little bit more continuous, like you see here. By the end of this video, we're going to get a thickness distribution that looks like this. And then by the very end of the video, this is what our final P shells look like. So you can see that here at this free end of this coupon, if you will, we have a very thin P shell. Here at the hole, we have a somewhat thicker thickness for the P shell. And then here at the fixed end, we have a very thick P shell entry, if you will. Now, a quick comment about the load cases. We fix one end of the open hole coupon, and then at the other free end, we apply our two loads. So we're going to have a load in tension, and then in the second load case, we're going to have a transversal load. Now, I have not rehearsed this. I practiced it a little, but I haven't really rehearsed this, so this is going to be very rough around the edges, but I thought that it's worth getting this video out there, so I decided to take some time today to make the video. Okay, so let's go ahead and get started today. Let's go ahead and start with our bulk data file. Now, I'm assuming that you have your own structure that you want to optimize, and today we're only going to consider the scenario where you have P shell entries. Again, we don't want to use topometry optimization for this. So we're going to get a very poor solution, if you will. And before I go ahead and continue on, let me go ahead and write what my optimization problem statement is. We want to minimize the mass, constrain the von Mises stresses for each element at Z1 and Z2. So Z1 and Z2 are going to be the bottom and top, respectively, of your P shell thickness. So you can imagine here's the von Mises stress for both the top and the bottom. Here I've selected max of VM1 and VM2. If I want to know what the von Mises stress is of the bottom, I can select this field, VM1. And then what I can do here, go to Fem label. I can turn on what's called the... Oh, I don't know if that actually works. Let's see if it works. Display element coordinate system. Nope. Orientation vectors. Oh, right. So here, I forgot where it was. Here in this post-processor panel, there's an option, display directions. When you turn that on, you get the material coordinate system for each element. And here, the blue indicates the direction of the positive thickness, if you will. So you can imagine that this blue here on top is the positive Z, or the Z2, and then the negative Z, which would be down here, this would be the Z1, or the bottom of the thickness. So here, this is the bottom, and then this is the top of the thickness. So you can think that all these different P shells, there's a top thickness, and then there's a bottom of the thickness, and here, that's what we're looking at right now. We're looking at the VM1, or the bottom von Mises stress, and then here VM2, this is going to be the von Mises stress of the top. Okay then, so here, this is what our constraints are. We're constraining the von Mises stress for each element at the top and bottom. And then what about our variables? This is what we're going to do. We're not going to do a element by element thickness optimization. That is not what we're going to do. This is what we're going to do. We're going to take the von Mises stress contours like you see here, and then here where we have the various lines, if you will, the contour lines, if you will, this is what we're going to use to create our shapes for the thickness distribution. So here, if I take this example and I zoom out a little, you can see that these lines for the different P-shell entries, these are the different contours on the von Mises stress and distribution contour. So that's what we're going to do. I'm going to walk you through how to do this. Now, this is based on a procedure that's outlined at theengineeringlab.com. If you go to that website, there is a section called Composite Laminate Optimization Tutorials. This procedure is intended to be used for P-comp entries, so if you're working with a composite. But if you are aware of some details, which I'll discuss in this video, you'll realize that the same procedure that can be used for P-comp entries can also be used for P-shell entries. So again, by the end of the video, we're going to start off with something like this. So here's our coupon. We don't know what the thickness distribution should be, but by the end of this video, we're going to end off with this thickness distribution you see here. So approximately, we're going to have about 6 P-shell entries. And this is all based on the procedure that's outlined here at theengineeringlab.com in the Composite Laminate Optimization Tutorial section. Now, let's go ahead and get started. Here's the bulk data file. Let's go ahead and look at this. Okay. This is what we want to modify first. Now, you might have a bunch of P-shell entries. Maybe you might have a bunch of P-comp entries. So let's go ahead and do this. Right now, all of my entries, they're using one P-comp entry. I do not want that. I want these to use, well, rather, I want them to use one P-comp entry with one P-shell or layer. Or rather, let me take a step back. What are we doing here? So your P-shell might look like this. P-shell 2 or some other ID, the material ID, and then the thickness of the P-shell. Notice that you can define a P-comp and it will give you the same stiffness like you had before. So here in this example, this is what you have. Here I'm using the symmetry option. So this composite, if you will, is going to have a total thickness of 0.25 because we're using the symmetry option. So whatever number of layers you have here, you doubled it, and then that gives you the total thickness of the P-comp. But here, I've calculated what the total thickness is. It's 0.25, and so that matches the thickness of this P-shell entry. Here, I'm using the same material. So here in the P-shell, it's 101, 101, 101. And here, for the P-comp layer, it's also 101. What I'm going to do then, I'm going to use a MAT1 entry, which is used to define an isotropic material. And here I'm using aluminum 6061 T6 or T91. So let's go ahead and put that here. Let's go ahead and use my Nastran styling here. So here are the units. We're working with millimeters, newtons, and megapascals. So again, realize that alternatively, instead of defining a P-shell entry, you can define a P-comp entry, and this will yield the same displacements, stresses, and so on and so on. Now, why do I have to use P-comp for this entire exercise? That's because we're using the workflow that's discussed on the website. This workflow was designed for P-comp entries, but it so happens that it also works with P-shell entries. So that's why for now, we're going to be dealing with only this P-comp entry. And then at the very end, we're going to convert all the final P-comp entries to P-shell. So here, what you see on this example is a layered optimization for these P-comp entries. But at the end, I don't want P-comp entries. I want single P-shell entries like you see here. So this step from here to here comes at the very bottom. So now let's go ahead and do this. Let's go ahead and copy and paste these entries here. Let's go ahead and copy that. to this file. And what I'm going to do is I'm just going to replace the old mat8 and the pcomp entries. And now I'm going to have this. So what is this giving me? This is giving me one pcomp entry with one layer, if you will. Since we're using symmetry, in total we have 2 layers and the total thickness is 0.25. Now let's go ahead and save this and let's go ahead and run it. But before I run it, let me output the results to the F06 file. Let me run this with Nastran. And there's one comment or detail we have to address. So let me see if I can get that here. Print, and let me make sure I'm in the right directory. Print. What I should get here are the stresses for this, so that's what I'm trying to get. Oh, right. Did I get a fatal here? Let's see if we got a fatal. Let me go ahead and search for fatal. Okay, I did not get that. Let me run this again. Something is a little off here. What I should get in this file now are stresses. Oh, right. So this is what's going on. I don't get ply stresses. And that's a problem for us. I'm not clear on... Oh, right. So here, if you look at this field, before it said no, so do not output the layer stresses, but let me say yes, output the layer stresses. So let's go ahead and rerun this. And then if we look in the F06 file, we should get a lot more data. Now, here's the problem. At the end of this optimization, or throughout this optimization, we want to optimize this isotropic material, but Nastran is outputting results as if I was dealing with layers in a composite. So here for element 1429, I get outputs, ply stresses at the midplane of layer 1 and 2. This is not what I want. So what I can do here is use this entry, param no comps -1. So if I go here and I put this in the bulk data section, instead of giving me layer stresses, it's going to give me stresses as if I was using isotropic material. So let's go ahead and run Nastran again. And so here are the new stresses. I get stresses for the Z1 and Z2 of the element, so the bottom and the top of the thickness. These first 2 rows are for the center of the element, and then the next 8 rows are for the corners of the element. So here there's a node 1 of the element, node 2, node 3, and node 4. Here I'm only going to consider the von Mises stresses at the center of the elements. So that was one additional thing we wanted to do. We wanted to suppress the stress output for the layers, and we just wanted the regular stresses as if we were using an P-shell entry with an isotropic material. Okay then, so let's go ahead and do this. Okay, let me go through my list. Let me make sure I'm doing everything right. Okay, let's go ahead and do this. Let's go ahead and configure a dummy topometry optimization. So let's go ahead and see how to get there. Let me turn off my bookmarks. I don't want that to be displayed. Hide bookmark bar. Perfect. Okay then. So here, we're going to open the Sol 200 web app. We're going to go to optimization. We're going to go to that directory. We're going to select that bulk data file, and we're going to click on topometry, click on the 1 thickness, which is here, and then we're going to go to the objective and select a weight objective, and then we're going to go to the exporter, click download the files, and then this is going to be our dummy topometry optimization. Now, the reason I'm calling it a dummy topometry optimization is because we are not actually going to perform a topometry optimization. We only need the tomvar entries that are in the bulk data file. So if we look at the design model BDF file, you can see that we have a tom bar here. That's what I need to go forward. Now, again, we are not going to perform the topometry optimization. The next thing I need is the following. So here, I have a stress contour for the von Mises stresses, and this is for subcase 2 for the top of the thickness, if you will. And then this is going to be the von Mises stress for the bottom of the thickness. Let's go ahead and look at load case 1. And this is going to be the von Mises stress for the bottom and then the top, which I believe were similar. Now, what I need to do, I need to find the maximum von Mises stress for both the top and the bottom, which would be something like this maybe. And I need to find the max for all the load cases. You can do this with Patran. You can create your own script. And in today's tutorial, what I've done is I created my own script that does this. So let's go ahead and jump to the script. So that is the script. I'll briefly go over it. So basically, this is what we do. We supply the h5 file as the first argument for this function. And then in the second argument, we supply the data set that contains the stresses for the elements. So that would be the Nastran result elemental stress quad CN dataset. And then what file do we want to write out the stresses to? Model.apply 0001. So that's going to run this function. So what it's going to do in these first few lines, it's going to access that data set. And then we're going to go line by line. We're going to compute the von Mises stress because the H5 file does not contain the von Mises stresses. It only contains the stresses in the X and the Y direction and the shear stresses, TX, Y. So what we're going to do, we're going to take those values. We're going to compute the von Mises stress for the bottom of the thickness and then the top of the thickness. We're going to store all of these stresses. And then at some point, which would be this part here of the Python script, we're going to take the maximum von Mises stress for every element, for the bottom and the top, and for load cases 1 and 2. Now, once we have the maximum, we write out the text file. And then let's go ahead and run this script. And first, let's go ahead and make sure I am where I want to be. So here, maybe we'll dump the data here. So I'm going to modify my script. I'm going to say output this data to this directory. So that's going to be my working directory. So normally when you run Python, so say I want to say Python app.py, the current directory is your working directory. But here I'm going to say, you know what? This is my working directory. This is the H5 file that I want to use. So let's go ahead and copy and paste it here. And now let's run it. So this script is actually a little slow, so give us some time. Once it's done, go to that working directory and you're going to have a new ply file. So what this ply has is the element ID followed by a 0 marker, and then on the next line is the corresponding von Mises stress, which is the maximum of load cases 1 and 2 for each element for the bottom and top of the thickness. And this has been done for every element. Now, in the workshops, I walk you through how to do this with Patran, but I realized, you know what? For today's exercise, it's actually faster if we just do it with Python, so that's what I went ahead and did. So another comment about this ply file. This ply file has the same format that you would get after a topometry optimization. So a topometry optimization would give you this. What we went ahead and did, we created this dummy ply file that contains the von Mises stress contours, if you will. So now what I can do, I can now go to the viewer and I can put everything together. So let's go ahead and do that. We'll go ahead and take the topometry optimization bulk data files. Okay, let's go ahead and make sure that imported. And then we're going to go to the topometry section here at the bottom left. We're going to select that ply file and we're going to upload it. Now, today we're only working with one pcomp entry. If you have multiple pcomp entries, the procedure is the same. You would just select a different pcomp entry and go about your process. So as an example, say you had p shell 1, p shell 2, and p shell 3. What you would do is you would replace those p shell entries with these pcomp entries. So here, let's go ahead and write some down here. So maybe you would have pcomp 1, pcomp 2, and pcomp 3. So you would just replace all those p shells with these pcomps. Remember, these p shells are equivalent to these pcomps, as I mentioned earlier in the video. So you would replace each pcomp, and then here you would find 3 pcomps available in this pull down, but today we're only working with 1 pcomp. Now, here in the apply shapes option, let's go ahead and move this a little to the left. And let me change the background maybe. There we go. Here, I'm going to click on this layer, the plus icon. I'm going to move the slider. So here in blue, if this was a pcomp, this would be the shape of my layer or my ply. This is using the von Mises stress values to split or cut the ply or the layer, if you will. So this is what I'm going to do. I'm going to work with, I don't know, and this is one of the tricky parts about this procedure. You don't know exactly where the beginning and end of your plies would be. So what we're going to do is we're going to create these candidate layers. So layer 1, 2, 3, and 4. And then we're going to go ahead and just run apply number optimization or a layer number optimization. And we're going to let the optimizer prioritize different shapes for us. So actually, let me do this. Let me see what we got here. You know what? I originally was going to go through this process of like tailoring the different shapes to my liking, but you know, to keep it quick for now, I'm just going to keep what I get right now. So remember, this is following the contours of the von Mises stress distribution. So let's go ahead and look at that right now. We're looking at the max von Mises stress here. So you can imagine that there are different contours. And then if we flip due to the different candidates, if you will, this is what it looks like. And then I think I'm just going to leave it there for now. Maybe later on towards the end of the video, I'll come back to this. But for now, I'll leave that as is. Now here, we're going to just supply some dummy thicknesses. So I think, all right, I need to create one layer. This is probably the most important layer. Make sure you have at least one layer that spans the entire coupon, if you will, your entire structure. Now here, I'm just going to say that all of these are going to have this thickness, if you will. Let me go ahead and look at this gply ID. Let me make sure I'm doing all of this right. Yeah, I guess we could optimize that. Okay, initial number of plies. Let's go and look at this. So let's look at our pcomp G zones, if you will. Oh, I realized my tool here is acting a little odd. But here you can see that these are the different pcomp G entries, if you will. You can imagine that there are different layers that are stacked on top of each other. So that's why we have different zones. Towards the end, these pcomp entries are going to be converted to p-shell entries. Now let's go ahead and exit this. Let me make sure I'm doing everything correctly here. So I want to optimize layer 110. Actually, maybe we'll delete that last layer. So the first layer is this one. Yeah, you know what? We'll do this. We'll leave this layer untouched. We are not going to perform a thickness optimization for that layer. We're going to leave it as is. but we're going to perform a apply number optimization for the other layers. And when I'm saying apply numbers, remember that we're just going to stack layer and layer and layer like we are here. All of these layers are aluminum. So this is what I mean when I say apply number or layer number optimization. I'm just stacking layers of aluminum again and again. And you can see that different regions of this model have different numbers of layers of aluminum. And then towards the very end of the video, I convert those P-comp entries to P-shells, and then that's the end of our exercise. So that's what I'm doing here. I'm performing a layer number optimization for different number of layers of aluminum. So now let me look here at these entries. Things look good. You can see that we have some bulk data entries for the apply number optimization. We have our new P-comp G entries, and at the very end, we get an update that all the 2D elements have been updated. Remember that the C-quad 4 entry has a field for the element ID and then a field for the P-show or the P-comp ID. So I'll call it PID. So before, all of these were pointing to P-comp 1, I believe. But now all of these entries are going to be pointing to different P-comp entries, P-comp 9 and so on and so on. That would be these P-comp G entries that you see here. So we have 2 through 7 here. So let me do this. Let me save this. And then let me go to new entries and click download. And we'll call this new directory apply shape output. Or here I'll call it layer number optimization output. No. I'll call it layer shape output for now. It's not complete. So let's go ahead and extract this. Let's look inside. We get this new file, design P-comp Gs. If you look in here, all the new P-comp G entries are here. And if we look in the model bulk data file, all the element or PIDs have been updated. All of these used to be 1, but now they're using the new P-comp G entries 2, 3, 4, all the way through 7. Now what we need to do here, we need to go to the home page and we need to upload these files. So let's go ahead and upload these files right now. What we need to add now are the constraints for the von Mises stress. So here are my apply number variables. Here what we're saying for these apply number variables range between a fractional apply number. So you can think that you want to let the number of plies range between 1 ply and 100 plies. Towards the end of the video, I'll say why it's a good idea to start with a very small fraction instead of a 1 ply as a lower bound. Now, our objective is the same as before. It's still a weight, minimize the weight objective. Now, what about our constraints? Remember that the F06 file is outputting stresses as if we were using a P-shell entry. We are not dealing with layer stresses. So here, and this is because we're using the param no comps -1. So since we disabled the apply stress or the layer stress output, we get normal quad CN stresses. So we can actually constrain, I forget what it is, but R type equals stress. We can use this one. If you did not have this entry, so if it was commented as an example, so here it's commented, so it's ignored, you would need to use, I think it's called C stress. So if you had regular layer stress output, you would need to use C stress. But we disabled layer output, so we can use the stress response type. So here, let's go ahead and click 2 entries. And here, the upper bound of this is going to be, let's go ahead and see, aluminum, mechanical properties. I forgot what the mechanical properties of this were. Oh, great. I can't find it. Aluminum 6061. Ah, here it is. So I want to get the yield stress for this. Let's go ahead and look here. Tensile yield strength. Oh, was it this? Okay, let me pause the video for a quick moment. So right now I'm looking at the bulk data files for my previous attempt at this exercise. So let's go ahead and see if I can find what's going on here. Here it is. So here the yield stress that I'm using are 395 megapascals, and I actually don't know where that value came from. Oh, you know what? I might be using... All right, I think I'm using a different type of aluminum actually. Let me pause again for a quick moment. Okay, I know where the discrepancy came from. I'm actually not using T6. I'm using T91. So I think if I look for the value here, okay, here, perfect. This is where I got the yield strength, 395. So we're going to go back here. We're going to say the von Mises stress is not allowed to go above 395 megapascals. And then here we have to do a workaround. So we're going to manually change a few things here. Right now, it's only allowing me to select P-comp entries, but I need to access the hidden P-shell entry. Now, when you define a P-comp or a P-comp G entry, Nastran internally builds an equivalent P-shell entry. And then if you turned on the correct setting, which I should close some of these items here because this is getting very crowded. So going back here, whenever you build a P-comp or a P-comp G entry, Nastran internally builds a P-shell entry, and it uses the P-shell entry to build the stiffness for that laminate. Also, you would get stresses, but since you're working with a P-comp, you get no stresses. But the exception is this. Exception, if you use this, then you do get stresses. You get layer stresses. So here, when we go back to this section, it wants me to select a P-comp. That's not what I want. So what I'm going to do here, I'm going to manually type in P-shell. And for the P-shell IDs here in the ATTI field, these are going to be the P-comp G IDs that you find here. So let's go ahead and open the design P-comp G's entry. So here at P-comp G 2, 3 through 7. So internally, Nastran has P-shell 2, P-shell 3, P-shell 4. You don't see these entries, but they're there. So let's go ahead and go back here. 2, 3, 4, 5, 6, and 7, I believe it was. Okay. So here I get an error saying that, hey, this P-shell 2, 3 doesn't exist. It does not exist in the bulk data files. It exists internally when Nastran runs. So we're going to ignore the error. And then we're going to go ahead and type in P-shell here in the P-type column. And now what about the element type? We want the von Mises stress. We know we're working with C quad 4 element 144. So we're going to select that element. And the reason we know this, very early on in the video, we looked at the stresses for the elements. We got stresses for both the center of the element and the corners. So that was corresponding to C quad 144. If you only had stresses at the center of the element, you're working with C quad 4 element 33. So here also you get the corner output comment here. So again, it's element 144 here. Now, for the item code, we want the von Mises stress at the bottom of the thickness and the top of the thickness. So then if we go to the subcases section, we're going to say, hey, take this von Mises stress for the bottom and the top and assign it to both load cases. I go to the exporter. I ignore this error. Remember, this is this one error here. We know these P-shell entries exist, so we'll go ahead and click download files. Now I'm ready for the layer number optimization. So let's go ahead and type in for here, layer number optimization. We're going to extract the contents and let's go ahead and see if this works. Let's go ahead and run Nastran and let's go ahead and see what's going on here. All right, let me unzip the file. I'm using Linux. So what you would do is you would open the command line and type in the name of the shell script or the script, and then click enter. But here, since I am in my development environment, I'm going to use my own method of running Nastran. So here we're running Nastran with the web app. If you were on Windows, you would just double click the button that says Start MSC Nastran. It would open this page. And then after a few design cycles, we should see a converged solution. So let's go ahead and talk about the results, because here I see that I've converged. Okay, this is looking really good. Let me do this. Let's talk about these ply number variables for a quick moment. So here, let's look at one of the shapes first. Let's look at this shape. So this is going to be Y1. It's not labeled here. It's labeled on the next table. So here, it's ordering your variables as follows. This would be Y1, Y2, Y3, Y4, Y5, 6. And then here I have variables Y1 through Y6. This column gives me more details on the variable. So here as an example, this is corresponding to gply IDs 11,000, or what is this? Or 112 and 211.2. So let me take a step back and say this. For this layer, how many layers of aluminum do we need? Here, it's telling me that at the very end, and Y1 is going to be here, I need 3 layers for that aluminum. So you can go through this process, say for the 6th layer, let's go ahead and turn on that layer. Let's take layer 5 as an example. Let's look at layer 5. So that would be Y5. I need a fractional ply. So I need less than 1 ply. So this could be an indication that, hey, this ply really, you don't need this ply. Maybe you can actually remove it and you would be okay. So that's what this is telling me. Let's look at Y4. Y4, it's also telling me that, hey, this ply, we think you need 0.1 or 0.2 of a ply. So this is effectively negligible. You can actually ignore these different shapes. So this is what we're going to do. We're going to open the viewer again. When you run this, you get this new directory called workspace C. This has automatically updated all the bulk data entries to take into account the various number of aluminum layers, if you will. So let's go ahead and go back here. And now let's go ahead and display only the pcompg entries. So let's go ahead and display at most 500 rows. Let's turn on the thickness distributions. Here we go. So now we have a result. So let's go ahead and look at, let me do this. Let me reset the table maybe. Let's look at a gply. Let me look at gply ID 116001. Let's go ahead and turn that on and see what that looks like. Actually, I don't see the, oh, here it is. So that would be this layer. So let's go ahead and see if we can find that variable number. So we're going to copy that 116. We're going to go back here, and that is Y5. So let's go ahead and zoom out a little. So here it's performed this rounding procedure. 0.7 is still pretty high, so it's rounded the ply number or layer number to 1. So that's why when we look at this, we only have 1. Now, what about this other layer, 114? You can see that we've actually stacked 3 layers of aluminum. So let's go ahead and look at that. So zoom out a little. So here are my 3 layers. And then sometimes it helps to change the coloring. So I think this will be this one here. So we have 3 layers of aluminum here. So let's copy that 114. Let's go ahead and search for 114. That would be this variable. So here it's telling me, hey, 3 layers of aluminum. So we have 3 layers here. But now what about this variable? At the end we got, which one was it? Let me see if I can find it again. There was one variable that was really low. So Y4 was a really small variable. So at the end of the optimization for Y4, it said that, hey, you need 0.2 of a layer. So it's negligible. So what the process does, it will automatically remove those negligible layers. So if we look for layer 115, it's not here. It's automatically removed that layer. So if we look for that layer, I believe that layer was, here, let's go ahead and display that layer. 1, 2, 3, 4, and 5. I believe it was this layer. Oh, right. So it was 115. It's absent. So the optimizer took a look at this layer candidate. It said, you know what? I need 0.2 of apply or layer. So you know what? I'm going to remove this layer from your final thickness. And that's what it's done. Now, this is what we're going to do. Let's go ahead and see if we can do another thing. Let's look at these results. Let me make sure that we have a feasible design. We want to make sure it's close to 0 or negative at the end. Perfect. We actually have a negative normalized constraint, so we should expect all the results to be okay. Now, you might be tempted to say, hey, I want to look at what those results are now. Let's go ahead and run this. Right, so let's go ahead and run Nastran, and you know what? I did not want that, so maybe let me go ahead and clean this up. So let me turn off Sol 200. I'm going to now switch back to a linear statics analysis. And here, let me turn off this echo that was automatically inserted. Let's go ahead and run it real quick. I want to make sure that this bulk data file runs okay. So that's what we're doing right now. And then I got a lot of output, so maybe I don't want that. Let's go ahead and go back here and say plot. And let's rerun this again. You can see in the F06 file, I have a lot of stress output. So here I've set plot instead of print. Let's go ahead and run Nastran. And then now let me go ahead and make sure I have no user fatal messages. Okay, that looks good. Let's go ahead and clear some of these objects. Okay, so what's next? We want to look at what the stress distribution looks like for this example. So this is what we're going to do. We are going to do the following. Let me see if I can do this. We're going to copy this directory, and we're going to call it workspace CP shell. We're going to open it. We're going to open this file. And we're going to create 5 P shell entries. So this is the part of the video where we have this. We have various layers, and I think it might be worth showing it here. So let's go ahead and reset all of this. Let me show you only the P comps. Let's go ahead and show you all the layers here. So now we have different P comps with multiple layers of aluminum. So you can think of it as this spot in the video. Now what we want to do is we want to go back to P shell entries. So how do we do that? So what we're going to do here, let me copy this template that I had. We're going to create multiple P shell entries. So here, let's go ahead and create those 5. So for this first pcomp G2 entry, we're going to replace it with P shell 2. So what we're going to do, we're going to take the thickness, and let me go ahead and open a spreadsheet program. And we're going to find what the total thickness is for that layer. So here we see that it's 1.25. So here, let's go ahead and type in 1.25 here. When you select different rows in Excel, here at the bottom bar, it will tell you what the sum is of those selected rows. So what I'm going to do here, I'm just going to select all these different columns, and then I'm going to paste it in Excel. And so what I'm going to do is I'm going to select all these rows. So this is going to be a total thickness here at the bottom of 3.5. So let's go ahead and write 3.5 for this P shell entry, and let's go ahead and repeat that for the next P comp entry. So here we have a total thickness of 3.25. So let's go ahead and type in 3.25. And then here, let's go ahead and repeat the process here. 3.25 again. And then here for this next one, 2.5. And then for the next P comp, we have a total thickness of 2. And then just to repeat the first P comp, when we select those rows, we should get 1.25 like we did before. Okay then. So now we've manually converted these P comp G entries back to P shell. So let's comment those entries so they're no longer considered for this analysis. Now, what's there left to do? Let's go ahead and run this file. Let's go ahead and run Nastran again. What we're going to do now, we're going to move this to the other side, so to the right side. And we're going to go back here and we're going to open the previous F06 file. Now, what you should have are the same mass and strain energy if you did everything correctly. So here on the left, these are the entries. This is the result when you use P comp entries. So if we look at the strain energy or the work, this is what we have. So these work values, if you will, this is when we use P comp G entries. This is the result at the very end of the layer number optimization. So this is what we got. We get these external work numbers, and then we have a mass. Now what I've done, I've taken these P comp G entries and I've made them P shell entries here on the right. Now remember, these entries are equivalent. Here on the left, these are layers of aluminum. I've taken the total thickness and then I've expressed it as a P shell entry. So both of these entries are all using aluminum with the same thicknesses. When I run Nastran for this scenario where I use P shell entries, I should get the same external work values. So here, let's look at the external work here on the left and right. And you can see that we actually have the same values. So when I use P comp G and P shell, I get identical values. Let's make sure the mass is aligned also. Here, I get that the mass is 2.86, and that matches the mass here on the right. Perfect. So we're done. I have successfully determined an optimal thickness distribution for this coupon with 2 load cases. Now, going back to the slide, remember, if you try to do the same process with topometry optimization, you're going to get a discontinuous thickness distribution. This happens when you do the following. Let me see if I still have that open actually. Let's go ahead and look here. Here's my original problem statement. So here, let me do this. Optimization problem statement for topometry optimization. So here, what do we do? We wanted to minimize the weight, constrain the von Mises stresses, and then here for the variables, element by element thickness variables. So this is a tombar entry / topometry optimization. But we've already done this before. We get discontinuous solutions. There's no spell checker in Notepad, so some of these words might be misspelled. So here again, if you're working with element constraints. Here we're working with stress constraints on each element. This will always give you a discontinuous answer. On the other hand, if you had more global constraints, so say you were constraining node deflections, this is no longer an element by element constraint. This is more of a global constraint, if you will. The response is more, it's not as related to the elements as what I want to say. This will give you a continuous solution. So it's the fact that we're constraining element quantities that produces this discontinuous solution. Here, what we went ahead and did, we took the stress contours and we built our layer shapes to align to these stress contours. And then at the very end, this is our new result. Let me actually show you what the new result looks like. So let me go ahead and take the new bulk data files in the P shell directory and let me upload them. And let me show you the thickness now. So this is the new thickness of our coupon. You can see that at the free end, it's determined that I really don't need a lot of thickness here. And then here towards the fixed end, you can see that it's used more thickness here at the fixed end. And then what about the hole? Here, the hole, it really didn't do a lot. But in a moment, I'm actually going to produce better layers in the next example. So one quick thing about this optimization, let's confirm that we're under the yield stress. So if you remember, the yield stress was about 395 megapascals. If we look at the max normalized constraint, here it's negative, so we're a little under 395. So let's go ahead and confirm that here. So let's go ahead and select the stress data set. Let's look at load case 1. And let's make sure we're looking at the von Mises stresses. Here we'll use the max operator. So display the maximum stress for the bottom and top von Mises stress. So here the maximum stress is about 10 megapascal or 108 megapascals. What about load case 2? What does that look like? So let's go ahead and select maximum VM V2. And let's look at the maximum von Mises stress. So the maximum von Mises stress here is 370 megapascals, which is a little under the yield strength of 395 megapascals. And here it's negative, so we were expecting it to be a little under 395. Now, you'll notice a few things. The maximum von Mises stress is no longer at the root or the fixed end of the coupon. The maximum von Mises stress is no longer at the ring of the hole. Normally you would get a stress concentration here, but that's actually not happening. What is happening, we're getting a stress concentration here at one of the layers. So if we go back to the viewer, I believe we're getting a stress concentration somewhere here in the model. So what you could do when you manufacture this, you could just smooth it out. I don't know what a manufacturing method you would use, but you see all these jagged edges. You wouldn't actually use jagged edges in your final product. You would smooth these out. So you would actually reduce the stress even more once you smooth out the edges. Alternatively, what you can do is the following. You can say, you know what? I'm going to hold this optimization to the side. What I'm going to do now, I'm going to go back here. I'm going to create even more candidate layers for the aluminum layers. So this was my first layer, my second candidate layer, my third, fourth, and fifth. What I'm going to do now is I'm going to do a little bit of experimentation. Now, in a perfect world, maybe in 50 years, someone will build an algorithm that can automatically expand or move these boundaries of the shape automatically during the optimization procedure. So we don't have that today. It's up to us to create these shapes manually. We create these candidates and we let the layer number optimization prioritize the layers for us. So here what we're going to do is the following. let me go ahead and do this. Here, this layer isn't really doing much in my opinion, so let's go ahead and see if we can break it up a little. Okay, so here is a scenario where we have two possible layer shapes. One layer would be for the hole, and the other layer would be for this region. So what would I do here? Let me create a new layer and use almost the same threshold. And now let me go ahead and delete some of this layer. So here blue is the layer and gray is no layer. And now for this region, let's go ahead and smooth out the shape, if you will. Let's go ahead and use maybe 1. Let's go ahead and smooth this shape out. So we're going to create layers of aluminum for the holes, for the hole that looks like this. And now what about this other layer? So let's go ahead and remove layer around the hole. And let's smooth out this layer. Let's go ahead and do something like this maybe. And let's go ahead and look at our layers real quick. So this is one of the layers, another layer, and this other layer. Now let's create another one. Remember, this is almost a trial and error approach. So typically what I like to do is I like to create a lot of candidates. And then I do extensive layer number optimizations. So I let the optimizer pick which candidates are the most important. So here, I'm not going to create 10 candidates. I'm only going to create a few. I'll leave it up to you to experiment on your own. And then here, I know that it might be worth creating another layer here possibly. So let's go ahead and do something like this. And now let's go ahead and look at our PCOM-Gs. Oh, so there is something going on here. Let's go ahead and see if we can figure out what's going on. I think what was happening, there was a lingering element. Okay, perfect. So these are the shape candidates, if you will. If you want to, you can get more creative. So maybe you want to experiment with a shape like this. Let's go ahead and remove the material around the hole. So that might be another candidate. Maybe we want another candidate for the hole. Here, let's go ahead and clean up the shape around the hole. And then we're going to use the remove tool to remove some of the shape. So let's go ahead and do that here. And then let me increase the size of this sphere. Let me use 5. So the sphere gets bigger so I can delete or remove the material a lot faster. And now let's look at our PCOM-G zones. So these are the different candidate layers of aluminum that we have so far. We're down here. So let's go ahead and configure our layer number optimization. So here, I'll leave it up to you to decide how thick each aluminum layer is. Here I'm using 0.125 millimeters. Let me make sure I have my DV Pro and my DESVAR entries. Okay, everything looks okay here. Let me save the entries. So once this blue icon is here, you're good to go. Make sure here you have your DV Pro and your DESVAR entries. This only happens when you click Save New Entries. Let's go to Download and click Download. And one important thing I did, I left this top layer untouched. You'll notice that for the thickness apply input, it's empty. Make sure you leave the first box empty. And if we look at that layer, why do we want to leave it empty? We want this one layer that spans the entire coupon to be left as is. You don't want to accidentally have, or rather, you always want to make sure you have one layer that spans your entire structure. If you're not careful and you accidentally remove this entry, you could actually get gaps. So say at the end, something happened, you got this gap. There's no material there. That's because you forgot to add one layer for the entire model. So always have one layer for the entire model. Here, what I did was create this shape. and then I left that input box blank. Now let's go ahead and do this. I have a new directory. Let's go ahead and do this. We'll call this layer out shape output B. So we're repeating the process with these other candidates, if you will. Now let's go ahead and upload this to my web app. So like before, I need to add my von Mises stress constraints. So let's go ahead and jump to the constraint section. Let's go here and let's look at what our pcomp geometries are. So our pcomp geometries are going to be 8 through 15. So let's go here. Let's go ahead and move this to the side a little. 8, 9, 10, 11, 12, 13, 14, 15. And remember, we have top and bottom von Mises stress, and then the top or the upper bound is 395 megapascals. And then here we have to overwrite some of the options here. We use P shell. We're using C quad 4 144, this stress item code, and then the stress item code. And let me double check and make sure I'm doing this right. 8 through 15. Okay. Subcases, let's go ahead and assign these von Mises stresses to both load cases, and then let's leave the app with our new zip file. And here I'm going to call this 6 layer number optimization B. So let's go ahead and unzip this. Let's go ahead and run the optimization. So if you're on Windows, you would just double click the start MSC Nastran link, and that would start this whole optimization for you. So we're almost at the end of the video. This is what I'm going to do. I am going to give you all of these files that I'm working with today. I'm also going to create a Python script file. This is going to contain the Python code that I used today. So remember, this Python code outputs that ply.ply001 file. So here, let's go ahead and copy this Python script. Here, let's go ahead and paste it here. Let me save it and let me close it. So that's going to be included in the final files I provide you. Okay then, so here we had one problem. It's actually terminated because I exceeded the maximum number of design cycles. So here, let's make sure we're doing something here. Let's make sure that we are getting close to converged solutions. So here you can see that I'm getting close to, a feasible design. Now let me look here, run terminated. Okay, let's go ahead and repeat this. Let me increase the number of design cycles to 40. And let me redo this optimization. So if you want to repeat the optimization, delete all your result files and restart the start MSC Nastran button. So let's go ahead and give this a few moments. And this, I want to say there might be a problem with this optimization, but maybe not. So let's go ahead and look at what's going on. Let me describe why I think there might be a problem. Here at around 9 design cycles, you can see that it's kind of stuck here. It's not making any progress with the ply or layer number optimization. So it's stuck there. I don't know if it can escape the infeasible design space. So here it has not escaped the infeasible design space. So there are a few things you can do. Let me go ahead and remove these files and let me do this. I'm going to use something called the truss region. So what I'm going to do here, I think it's T region 1 to turn it on. So what the truss region does, here, let me show you what's going on here. During each design cycle, the variable is allowed to change only a certain amount. So say example, the variable starts at 5. Maybe it can only move at most 5 units. So the next variable is 10. The next variable is 15 and 20. See, the increments are 5. What the truss region does, it adjusts that step, if you will. So instead of 5, maybe let's say, hey, let's move by 10, or you know what, let's move by 1. That's what the trust region does. It automatically adjusts those move parameters. Here, I've performed the optimization again, and I still can't get a feasible design. So let's go ahead and do this. Here, let's go ahead and maybe start with a different number of layers, if you will. Here, I'm starting with a layer integer of 0.001, so that's a fraction of 1 layer. Let me start with 10 layers. Let me save that. Let's go ahead and rerun this. And remember, I'm trying to get a feasible design out of this. So let's see if we can get a feasible design from this. And I'm still not. So I must be doing something wrong. Oh, I think I know what I'm doing wrong. Let's go ahead and see if we can confirm this. Oh, here, pcomp G8. pcomp G8 only has this. That's not good. We made a mistake here somewhere. So let's go ahead and turn this on. pcomp A would be this layer. Oh, that's what's going on. Okay. So this is what's going on. It might be worth, how do I go about this? Here, let me just look at this pcomp G entry. Look at the thickness. It's 0.25 millimeters. That's a very, very small thickness, if you will. The von Mises stresses in these group of elements is very high, so that's why I'm getting the problem right now. Here, I made the mistake of not creating the fully continuous layer properly. So what I'm going to do here, I'm going to create another layer. And let me show you what this layer looks like. This layer is going to be fully continuous. And then here, let me configure the thickness. And that should yield a better solution for us. So let's go ahead and save the entries, go to download and download those bulk data files. And I guess there was a mistake here somewhere. Let me see if I can find it. I think it was here actually. One of my files has been modified, so that's why this is happening. So let me see if I can find it. I think it was this one. Let's see. The one thing I don't want to do is I don't want to redo this whole exercise, so that's why. Let me look at this. File design. This one was modified. If you modify one of the original bulk data entries, you'll get that error. So that's why I want to hunt down that bulk data file. Nope, I think I may have. Is it this one? Let's see if it's this one. Nope, I have to redo this whole exercise. So let me delete some of this. That's okay. You get to see me do this all over again. So let's go ahead and do this. Let's go to that dummy topometry optimization set of files. Let's go ahead and upload that. Let's go into topometry. Let's select that ply file. And now I can create my shapes again. So let's go ahead and do that. So we'll create these shapes. Maybe the last shape will be a fully continuous shape like this one. This one, we'll go ahead and make it something like that. The next shape will look maybe like that. Now here's where I get a little creative. We'll maybe do something like that. And for this next one, maybe we'll use this exciting shape here. So let's go ahead and do this. Let's go ahead and make sure we fill in these voids. And we'll go ahead and make sure we fill in these voids with the shape. Let's go ahead and look at this candidate. Maybe I don't want all these elements here to have this layer. So let's go ahead and remove that. And let's go ahead and clean up this layer. Let's go ahead and see if we can do this. with the pick sphere. It's going to remove these lingering pieces of layer. Let's go to the next one. Here, what I'm going to do is remove this material from the hole and maybe leave it here. And you know what? This is too rough for my liking, so let's go ahead and do this. Let's go ahead and trim some of the material. So let's go ahead and look at our candidates so far. So it'll be this, 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 this. So what do we do here? Maybe we'll go ahead and create this other shape. Let's go ahead and fill in this material. So actually, I'm going to create a few more candidates than before. And the goal is to hopefully produce something that weighs less than before. Okay, now here, let's go ahead and make sure I got my bearings right. Let's go ahead and fill in these elements. And let's remove this. So let's quickly recap our candidates. This is one candidate of aluminum layer, another candidate of aluminum layer, another candidate, another one. This one's kind of different. We want to experiment a little here. I don't want this material, so let's go ahead and see if we can remove it. And then your last layer, make sure you have at least one continuous layer. That's where I made a mistake before, and for certain reasons it caused the Von-Mises stress to be really high. So make sure you include this one continuous layer as one of your candidates. Now let's look at the PCOM-G zones. This is what the PCOM-G zones look like. So here it's basically a collection of all the different candidates. And now let's go ahead and focus on our thickness is here. So 0.125. I don't recommend putting a thickness for the first layer. So here, let's go ahead and make sure we have our PCOM-G entries, and we have our DV Pro, our DesVar entries for the ply or layer number optimization. Let's save it. Let's go to download. So what we're going to do here, 5 and 6 were the failed experiment. So here we're going to say 7 layer shape output C. And let's go ahead and extract the contents of that. Let's go to the web app and let's go ahead and import these files so we can go ahead and create our Von-Mises stress constraints. And now the reason you have to go through this exercise is because this tool here, the optimization web app, has all the responses you need. So that's why we're coming here to finish up our preparation for the layer number optimization. So here you see me do this a few times, so I'm going to go through this really quickly. So P shell here and here, C quad 4 or 144, and then here, and then 395, and then what about the PCOM-G IDs? Let's go ahead and look here. So even though these are PCOM-G entries, internally Nastran is building P shell entries rather. There's a P shell 2, a P shell 3, a P shell 4, all the way through P shell 8. So here what we're going to do is type in P shell 2, 3, 4, 5, 6, 7, and 8. I'm going to copy this. So here let's recap what we did here. We're constraining the Von-Mises stress for the bottom and the top of P shell 2, 3, 4, 5, 6, 7, and 8. At most, the Von-Mises stress should be 395. For the subcases, we'll assign the sub constraints here and here. Let's download the bulk data files. And let's go ahead and we'll get a new directory. We'll call it A layer number optimization. And we will call this C. Okay, now this should work. Fingers crossed. So let's go ahead and let this run. And let me go ahead and start a new spreadsheet here. And then if this does not converge, okay, so something's going on here. I think we're still successful though. So let's look at a few things. Did we get a feasible design at the end? The final design has a max normalized constraint of negative 0.0498 or negative 0.05. It's negative. We have a feasible design. Why does my message look like this? Run terminated due to hard convergence at best compromised design. But then it says hard feasible discrete design. What's going on here? So let's go ahead and display the layer number variables. So for the first 12 design cycles, it's performing a continuous variable optimization. So if we look at design cycle 12, look at what our variables are. We get fractional values for the layer number variables. So we get 3.55. I should get an integer of maybe 3 or 4. Here for the next variable, 3.39. I think it might help if I zoom in. Here, again, I'm getting fractional values. I should be getting integers for the layer number variables. So what happens when you use discrete numbers, so here we go to the variable section. Here we specified, hey, at the very end, give me variable values that are one of these values. It's a list. So here you can either be 0.01, 0.02, so on and so on. You could be between 1 through 100. So 1 through 100 layers. Here it's performed the continuous variable optimization. And then at the very end, here it's not actually rounding off, but for today I'll say it's rounding. It's rounding the final variable values to this, 4, 4, 3, 2, 2. So even though this design cycle 12 was infeasible, so here is design cycle 12, here the max normalized constraint is positive 0.0233. Even though this continuous variable design cycle is infeasible, when it rounded off the variables to integers, I then get a feasible design. So that's why we get one message saying infeasible, and then the next message says, hey, at the end of the rounding, I get a feasible design. Great, perfect, we're almost there. Let's go ahead and do this. Let's go ahead and copy that directory, and we'll call this the P shell entry directory. So if you remember, the final bulk data files are all using pcomg entries. So what we need to do now, we need to convert those pcomg entries to p shell entries. And right now what I did was, a moment ago, all these bulk data files were set to sol 200. But now I'm towards the end. I want to perform a final validation analysis, so I switched it back to sol 101, a statics analysis. So here, let's go ahead and open the pcomgs, and then let me close some of these other text files just so we don't get confused. So like before, I need to create new p shell entries. So what I'm going to do here, I'm going to copy all of these thicknesses to my spreadsheet program here. And then what I'm going to do now, I need my template here. Let's see if I can find it. I'm looking for this p shell entry because now we want to convert those pcomgs back to p shells. Let's go ahead and do this and zoom out a little, and we go to pcom 8. So let's go ahead and create some entries here. 4, 5, 6, 7, and 8. 2, 3, 4, 5, 6, 7, and 8. Okay, let's start updating the thicknesses now. So here, these cells are for pcomg 8, so 3.75. And now what about the next one? We get 3.75 again. And then what about the next layer? Are all these 3.75? Oh no, this one's 3.5. And then here, let's go ahead and type in 4. And then for the next one, oh wow, this is actually producing, what looks like a thicker coupon. So let's go ahead and keep going here. 2, 2.0, and then for the last p shell, it's going to be this 1. Okay, so here are our final P-shell entries, and we're going to go ahead and comment these old PCOM-G entries. Let's do this. Let's go ahead and run these entries that have the P-shells, and let's run these bulk data files that have the PCOM-G entries. We want to make sure that the external work and the mass is the same for both. If it is, great. That's indication that we are properly converting the entries to P-shell. So let's go ahead and go down here. Okay, perfect. So if we look at the external work for both load cases, you can see that they're identical. So that's good. That means we've properly converted the PCOM-Gs back to P-shells. So here you can compare the values. And then let's compare one value I didn't compare before, the displacement. So here are the displacements. So you can see that the displacements are similar. Actually, they're a little, oh no, I'm looking at the wrong column. So if you look at the displacements in the 3 direction, so that would be the Z component or the 3rd degree of freedom, you can see that I'm getting about 13 millimeters of displacement for when I use PCOM-G entries and P-shell entries. And then if I look at the mass, the mass should be identical. And then I already remember the mass from before. The mass was about 2.0, and here we're getting a mass of about 3.0. So we're actually getting a heftier laminate or layer than before. So this is what I'm going to do. Let's go ahead and look at the new thickness distribution. So I think this was in this directory, the P-shell directory. Let's go ahead and look at what our new thickness distribution looks like. Let's go ahead and turn that on. And here, this is going to be study C. So that would be these ones with the trailing C or letter C at the end of the directories. And then we're going to look at 3 and 4. So that was the very first study at the first part of this tutorial. So that would be in this window. So let's go ahead and open that. So let's look at what's going on with the thickness distribution. All right, so it's because of this. That helped me out a little. So let's go ahead and hide some of this. So you can see one thing. This is a trial and error process. So I tried to use these cleaner shapes, if you will, for the aluminum layers, but this actually produced a heavier coupon, if you will. When I was more ambitious with the shapes of the layers, something like this, I was actually able to remove more material. So the message here is, when you're at this step, experimenting with your different shapes, feel free to create multiple candidates. And this involves some trial and error, some experimentation, if you will. But this is a lot better than using topometry optimization because, again, you get a discontinuous thickness distribution. This approach has worked well for us today. And then one last comment. You'll notice one thing with my layer number optimization. So here, let's go ahead and look at the results from before and after. So this is the results from the original layer number optimization. So maybe we'll move that here to the left. And then here on the right are the latest results for the layer number optimization. So let's go ahead and move this to the right. And let's look at the final mass. So the final mass here was about 2.86. Here the final mass was about 3.2. So again, the first optimization that we did with these layers, this produced the best design so far. I can continue experimenting with different shapes for the aluminum layers, and hopefully I can come up with a better shape. Unfortunately, we're not in the future. No one has developed a tool that automatically decides to expand the boundaries of the shapes. So here, what we have to do in this tool, we have to manually add or remove material for these shapes. Hopefully somebody in the future will do this automatically. The optimization might run like this. I do a layer number optimization for this layer shape. Is it good or not good? Okay, let me increase the number of layers. Let me increase the boundary. Is this better? Yes or no? No. Let's go ahead and keep increasing the layer. Is that better? Yes. Okay, let me go ahead and remove some elements. Is that just as good? Yes. Okay, we have a good optimal shape. We're not there yet. There's no algorithm that will expand the shape or contract the shape of your layers. We have to do that with these candidates. So once we have these candidates, we then go to the optimizer and we say, hey, for each of these candidates, determine what number of candidates do I need. At the end, I get these layer number variables, and it'll say, hey, for these 4, 3, and 2 layers, keep these layers. For this layer that has a fraction of 0.2 layers, it's negligible. Let's go ahead and remove that layer altogether. And that's what was done for the layers optimization. So let's go ahead and look at that. If we look at this and see if there are negligible layers. Oh, there is. Y6. So this layer was left out, and I'm wondering what layer that is. So let's go ahead and see if we can go back here and track down that layer. So it was this layer. So this layer, it said, you know what? You only need 0.01 of a full layer. Let's go ahead and just leave out this layer. That's what's being done internally. So if you look at the final model, I don't know if that's this model. No, it would be this one. Oh, it did include it in. But it's just some more details for you to keep in mind. One last comment. You notice one thing I did with the layer number variables. The layer number variables have to have integers at the very end, between 1 and 100. So 1 layer, 100 layers. At the very end of the optimization, I started with 0.01 layers. And you might be asking yourself, why am I starting with 0.01 instead of maybe 1 layer? Why am I doing this? Let me quickly detail why this is happening. So when you look at your design space, you have corners in the design space. You have an upper corner and a lower corner. So let me see if I can find an example for you today. Yeah, I think I might be able to. So let's go ahead and jump into one of my machine learning web apps here. So what I want to do is I want to show you physically what the upper and lower corner look like. So I'm going to perform a regression. I'm going to approximate this response with the Gaussian process model. I won't go into too much detail with what that is, but here, let me go ahead and jump here. This is what I want. So let me go ahead and hide some of this data. So here I have a variable x1 on the horizontal and then a variable x2 in the vertical. x1, say as an example, is allowed to range between -2. Well, here in this case, it looks like it's a -2.1. And it goes up to +2.1. And here for x2, it ranges between -1.1 and +1.1. If the variable, let me write this here. Say x1 is allowed to range between this, and then I think it was -1.1, -x2, and 1.1. So here, let's consider this number of variables. So I have -2.1 less than x1. So this is basically this design space. What does the upper corner look like? The upper corner is when x1 equals the upper bound and x2 equals its upper bound. So you can think that that would be the top right hand corner. And then we have a lower bound here at the bottom left. What does that look like? Here, for the sake of discussion, let's suppose that we're only dealing with 0.001. Why am I doing this? Maybe this is an area for a beam. Area should always be positive, so that's why we're only considering positive bounds. So here, what I think I can do, I can move this to, okay, perfect. Yeah, that helps me out a lot. So now here my bounds are 0, 2.2, and 0, 1.1. So the upper corner is when the variables are equal to the upper bounds. What does the lower corner look like? What's going to be in this case 0.0001, and the same thing for x2. So now let's go ahead and think of let's have a thought experiment. Let's say that the upper bound was very high. It was maybe 2000, and here I don't have enough data for 2000. But let's say it was really, really large, 2000 as an example. So here, let's go ahead and adjust this. 2000 millimeters as an example. Let's suppose that your optimization started here. It started at the upper corner. If you start at the upper corner of the design space, that optimizer has to travel all the way close to 0, 0. We know that the global solution is somewhere close to the lower corner of the design space. It is not here. I forgot what I was using. And oh yeah, I was using 2000 millimeters. We know that the global solution is nowhere near the upper corner. We know that the global solution is closer to the lower corner of the design space. So what I did in my optimization is I set the initial values, if you will, for the optimization. I think it was this value. And then I had multiple. And here my variables were y1 actually. What I did with my layer number optimization, I purposely set the variables to a very small value. So the starting point is close to the lower corner of the design space. It's in this region of the design space, close to the lower corner of the design space, where I know that the global optimum is. So that's why I start in this vicinity. If I started at the upper corner, the optimizer has to transverse all of this volume. And unfortunately, oftentimes, it'll converge to a local optimum that is suboptimal. So in my opinion, for this exercise, it's better to start towards the lower corner of the design space. That's why I set the variables really small. If we look back here, let's see if I can find that window. Here, let's go and zoom out. This is why the variables start at 0.01 and they don't start at 1. I want to start as close as possible to the origin. And then here, since I'm very close to the bottom left-hand corner of the design space, hopefully the optimizer can find a local solution that's close to the global optimum. So this strategy, I call it the inflation strategy. So you can think that the layers in the aluminum coupon, they first start off as being very thin. So I think I can show you that here. Perfect. Let's see if I can, right. So here, this is what my very starting aluminum layer looks like. It's very, very thin. So the optimizer is going to inflate the thickness for the different layers. So here's what that will look like. So here it's inflating, it's increasing the number of layers. This tends to yield a better solution. So again, I call this the inflation strategy. If you want to remember it, you can think that you're inflating a balloon. a balloon starts flat, but as you put more air in the balloon, it gets larger and larger, like you see here. So that was the last thing I wanted to leave you off with. So I think that's pretty much it. For those who want these files, I'll keep a copy on my desktop. So if you want to follow along this exercise with these files, just send me an email, and then I'd be more than glad to go ahead and give you a copy of these files. Let's go ahead and leave my contact information here. And let me just give you the final statement. If you're dealing with element constraints, you want to constrain the element stresses, strains, failure indices, apply stresses, apply strains. Do not do that with topometry optimization. You're going to get a result that's discontinuous like this. Use the contours. Use the contours to influence your candidate shapes. Then go through that layer number optimization. And then at the very end, convert back to p-shell entries like we did in this exercise. This will give you a better solution like we showed here, and these various examples that I showed throughout the video. So with that, I'll stop here. As always, thank you so much for watching. If you have any questions, as always, you're more than welcome to contact me here at this email address. Thank you.